Hi guys, Stupid Simple here, where I take topics that make me feel stupid and try and make them simple. Today is the second video in the series of videos on differentiation. If you missed the last one or want a recap about the proof and definition of what differentiation is, then you can find that video link below. If not, today we're going to be talking about the power rule. So let's get on straight onto that. The power rule is a quick and easy way to differentiate a function that you'll come across in any given question. By and large, it's relatively simple and it's much quicker than you would have found in the last video using the definition. If you recall last time, we took x squared as a pretty basic example and used the whole formal definition of the function of x plus h minus function of x all divided by h, and then took the limit as h went to 0 of that, and blah, 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 blah. There was a lot of steps. Then we got an answer, and it was absolutely fine, and it worked, but it was slow, it was difficult, and most importantly, it's just not practical, really. It's great maybe later on when you're trying to do some more advanced and trickier things to get an understanding of why you're doing a lot of the stuff we're doing, but for now, let's keep things easy and make things a bit quicker and faster. So, the power rule is quite simple. For any x that we're going to differentiate, it's going to be multiplied by some coefficient. Let's call that c, in fact. Let's make things easier here. Let's color code everything. We're going to have x multiplied by some coefficient c, and it will be to the power of some n. C and n are arbitrary. It doesn't matter at all. What we're going to do to differentiate using the power rule is quite simple. What we're going to do is we're going to take our value of n here, and we're going to throw it in front here. So we have an n times c as a coefficient timesing x, and then all we're going to do is take away 1 from the n. That's it. That is everything you have to do. Instead of using the whole definition that we found in the last video, instead we have 2 steps. Coefficient times the power minus 1. So let's give that an example. Let's take exactly as we had before. Let's use x squared as a relatively simple but fundamental example. We have x, let's do this. Let's color code everything exactly the way we have it here. We have x squared with a sneaky 1 times coefficient. The dot there just being a multiplication sign. All we're going to do is take this 2, multiply in front here by the coefficient. So we get 2 times 1 times x. And then we're going to minus 1 from the 2. That will give us 2 times 1 is 2. The x stays as an x. And 2 minus 1 up here gives us 1, which in terms of indices is just 2x. And that's all we're going to do. That's the power rule. It's quite simple, it's quite easy, but it can become tricky in more difficult cases. X squared is a great example to get started with, but it's not an exhaustive idea. Let's move up things a little bit at a time and see where we find ourselves. So let's go with something a bit trickier. Let's say, for sake of argument, with what we used last video, let's use 4x cubed, because we can at least go back to the last video then and check that our answers coincide. So we take our 3 and we put it out front here, and then we take away 1 from the 3. So that'll give us our x here. What is 3 times by 4 before we do the 1? 3 times by 4 is 12. And then 3 minus 1 is 2. That's all there is to it. This is fine. This works well. What then happens if we have multiple things? Let's say we have some line y equals x to the power of 5 minus 2 minus 2x cubed. We have 2 terms now. So that's fine. We just do exactly the same rule, but we do it to each of them individually. So in this case, the 5 comes down in front here, and then we'll take 1 away from it. And the 3 comes down into here, and then we'll take 1 away from it. Let's put this in different colors so it's clear. 5 minus 1, 3 minus 1. So, first things first, our differentiation, dy by dx, equals, well, we have a sneaky 1 up at the top here, 1 times. So 1 times 5 is 5, the x is still there, and 5 minus 1 is 4. We have a minus 2 in front of x, and minus 2 times 3 is minus 6. We put the x in, we minus 1 from the 3, and we get 2. And we're done. That's all there is to it. Again, this is great. We know how to do it in a simple case where we have some x to a power of something, and we know what to do when we have multiple of them. So let's increase the difficulty a little bit. Let's say that instead of a basic, simple situation where x is to the power of something that we're used to, let's try x to the minus 1. For those of you who aren't familiar with index notation, this is just equivalent to 1 divided by x. This will be important later. So we'll use the same rules as per usual. We take this multiplication, we take this power number here, and we take it over to the front, and then we minus 1 from it. It's the same rules even if it goes negative. So minus 1 times x is minus 1 times x. Minus 1 is minus 2, which equals minus x to the minus 2, which equals minus 1 divided by x squared, for anyone who's curious about how that works. It's the same logic, we've just got to go at it step by step. Now, what you'll notice that I've done in this example is I've moved between index notation, or x to the power of something up here, and what that actually means in terms of numbers, like 1 divided by x. And so that really is going to be what forms our first step in using the power rule. Consider for me, please, the following example. Y equals square root of x. I would like for you to differentiate that for me, please. I'll give you a moment, pause the video, go ahead and try it. Okay, if you've had a moment, great. Now, for those of you again who are comfortable with index notation, this is not a problem. But for those of you who aren't, let me know. I'll happily do a video on it myself. But we know that the square root of x in index notation is just x to the power of 1/2. From here, we can do the exact same rules as we've done before. We're going to take the 1/2 over here, and then we're going to minus 1 from the power. This gives us 1/2 up here, times by the 1 that would be hidden down here. Therefore, our dy by dx equals 1/2 times by x. And 1/2 minus 1 is just minus 1/2. And we're done. There's an argument to be made that we can now put this back into regular form. So that's 1 divided by 2 times by, now x is a minus, so it's going to be something over x. We have the power of minus 1/2, so you could argue a division by square root x, but surds don't really like to work out that way so well, so for now we'll just keep things in index form because it works and it's convenient if we want to find something else. Or we want to work with it more, say, oh, let's be mean here. Put some 2's up here, and now all of a sudden, this is not the case. If I put 2's up top, that means I'm asking for the second derivative of y. So let's go ahead and try and find that by keeping this in index form. By applying the exact same rules, give it a go yourself. I'll give you a couple seconds. Okay, if you've had a chance to try it, let's go ahead. If you haven't, follow along, and hopefully this will make sense. We'll apply the same logic as we have before, except now the second differential of 1/2 x to the minus 1/2 d squared y by dx squared, otherwise known as the second differential of y, is, well, we're going to take this minus 1/2 and multiply it by the 1/2, and then we're going to take away 1 from it. So minus 1/2 times 1/2 is minus 1/4. We bring our x back in, and then we take 1 from minus 1/2, which is, if you've got it, minus 3/2. And there we have it. That's all there is to it. Now, it's a bit less obvious what x to the power of minus 3/2 means relative to, say, x to the 1/2. But give it a little bit of thought. Tell me what you think that means in the comments if you're unsure, and I'll be happy to go over videos like this as well, maybe more in depth on what index notation really is. But this is all the power rule is. It's a simple way of differentiating, and it's much quicker than you'll have seen in using the definition. So let's go for a few more examples and get a bit trickier, shall we? Let's come down here, and let's say that my function of x equals 2 square root x plus 3 divided by x. And I want you to find f prime of x. I'm using different notation here because different textbooks and different exam boards might use different notations, so I'll try and be as broad as possible. F prime is just me asking you to differentiate this equation exactly the same as we've done before. Instead of calling it y, I'm calling it f, and the prime there just means differentiate. So I'll give you a few seconds, give it a go. Okay, if you've had a chance, great. If not, we'll do it together. So, as per usual, the very first step is to rearrange this into index notation. We have a 2 root x at the top. The 2 stays the same. Square root x, as we saw in the last example, is the same as x to the power of 1/2. Added to that, we have 3 divided by x. The exact same logic is going to apply. 3 is the coefficient here because we're multiplying the numerator, the top half, this one, not this one, this one, by 3. So that becomes 3x to the power of minus 1. Now that we're in an index notation, okay, this is strictly not true. F of x is still that. Now that we have index notation, we can form f prime of x is equal to, and we'll use the same rule as before, the power rule. We'll take the 1/2, multiply the 2, and we'll take the minus 1 here, and multiply the 3. So that gives us 1/2 times by 2 is 1 times by x. And over here we have minus 1 times 3, so that's a minus 3x. And then we'll take away 1 from each of the powers, as before. So that gives us 1/2 minus 1 is minus, what am I doing? Is minus 1/2, and minus 1 is minus 2. Hooray, fairly simple, right? Okay, so let's go in for a slightly harder example now on something that might be new to you or might be familiar, depending on your experience. Either way, let's go into it. For those of you who are familiar with the concept of e, we're going to have a look at e to the power of x. Now, as index rules will tell us, this is just equal to e to the times e times e times e, as many times as it will, well, x times to be precise. So knowing that, as a bit of background, and using what we learned in the last few examples, if I instead write this as my function of x is equal to e to the x, what is my function prime? I'll give you a few seconds to work that yourselves. Okay, cool. If you paused, how did it go? If you haven't, that's all right. We'll do it together. Let's see what we get. So we're going to apply the same rules, even though now on top there's an x and on the bottom there's no longer an x. The same logic still applies. What we're going to do first is we're going to take our power down to the front. So that will give us an x times by our e, which is the first thing that we're differentiating. And then we're going to take away 1 from the power, so x minus 1, which doesn't really have a huge amount of meaning since we don't know what x is. So it just stays exactly like that, x minus 1. Technically, this is now done. We've differentiated, hooray! But at the same time, we can make things a little bit simpler, because if you understand what indexes are, and you understand how they work, we can see that we're multiplying e by x, and e is a power of x minus 1. So we can absorb this x into the e again. Actually, for easiness of seeing that, let's put the x back into here, more closely way back up here, and now we have an x minus 1 plus 1, or plus another x, because e is in terms of x, and that just cancels both of them out. So the whole thing in total just equals e to the x. And this is a fun one that you might see in a few bits of maths and is quite useful to know ahead of time, is that d by dx of e to the x, I put no y there because I haven't said that y equals e to the x, I've just e to the x being any function I want. D by dx of e to the x equals e to the x. It doesn't change at all, which I think is pretty fun. It's pretty much, you can check this out yourself, but if you think of a graph with the function e to the x on it, it will look something like that, like a really tall exponential up. And if at any point on this you take the y coordinate on it, or the function coordinate, whatever we want to call this, oh, screw it, let's call it y. Bit messy, but whatever. Whatever point you find along this, let's call that point x would be bad choice, let's call it point star. The gradient of its tangent, let's zoom in a wee bit, the gradient of tangent of star, let's call it grad. The gradient of star equals the star. And the same goes for any point up the graph. It's a bit of a strange one, it's a bit of a unique one, but it's useful. And things that are maths that are useful are usually fun, and things that are fun are usually useful. But that's how that works. So let's go for one more example, something a bit trickier, something that you might see in an exam book, for example, and then we'll probably leave it there. So for now, let's try to find the gradient of the curve y equals, oh, what should we do? Let's say 12x squared plus e to the 2x minus 4 square root of x plus 8 over x squared minus x. Pretty long one, big question, but let's do what we can. Well, no, this is a bad question. Okay, let's finish the question because I'm asking for a gradient. Let's say at the point x equals 1. Okay, I'll give you a few minutes to give this a go yourself. Pause the video, try your best. If you're struggling, that's absolutely fine. We'll come back in a second, we'll work through it together, but I do recommend giving this a go. This is foundational, this is fundamental. So understand this, you'll be doing much better in later questions ahead of time. So I'll see you in a couple seconds. All right, welcome back. Hope you've given it a go. If you haven't, that's okay. We'll go through it together now. So first things first, step 1 is put everything into index form. We have y equals 12x squared is already in index form, so that's great. We can keep it as is. 12x squared. E to the 2x is also in index form, so we can keep that as is. So, 4 square root of x is not index form, so we're going to change that round to minus 4x to the power of a half. 8 divided by x squared is also not in index form, so we'll convert that into 8x to the minus 2. And minus x is in index form, technically, minus x. There is, I should preface, a sneaky hidden 1 there, which will, if you haven't seen this before, will come important very, very carefully, very soon. Now, we can differentiate dy by dx equals, we'll use the same logic as before, the 2 multiplies the 12 here, the 2x multiplies whatever's going on in front here, half multiplies the minus 4, minus 2 multiplies the 8, and the 1 multiplies the minus 1 here. Putting all of that together gives us 24x plus 2xe minus 2x minus 16x minus x. We then do the second part, the next part, which is taking 1 from each of the powers. So we do exactly that. 2 minus 1. 2 minus 1 is 1. 2x minus 1 is still 2x. A half minus 1 is minus a half. Minus 2 minus 1 is minus 3. And 1 minus 1 is 0. Anyone who's seen this now knows where I'm going with this. We can simplify things a little bit. X to the power of 1 is just x, so we have 24x plus, we can absorb this x into the e to the x. I realize now I didn't write the minus 1 here. My mistake, I apologize. So we can absorb the x back into this e to the 2x minus 1 here, and therefore that will give us 2x e to the 2x again. You'll notice in all differentiations of x here, v here, we can just differentiate the term up top, which in this case would give us a 2, and just put that on bottom as well. But that seems a bit more akin to another technique we'll see in the next video. For now, the logic still applies here. Minus 2x to the power of minus a half stays the same. Minus 16x to the minus 3 stays the same. And x to the power of 0, well, anything to the power of 0 equals 1. So therefore we have minus 1. And that's it. All we're going to do now is substitute 1 into all these values here, and we'll get our answer. So that's 24 times 1 is 1, plus 2e to the power of 2, minus 2 times by 1 to the power of minus 1/2. So that the minus means it's 1 divided by, and the 2 means it's the square root of 1. The square root of 1 is 1, and 1 divided by 1 is also 1, and 2 divided by 1, or 2 multiplied by 1, is still 2. This whole term just goes to 2, minus 2 therefore. Minus 16 times by 1 to the power of minus 3, 1 to the power of minus 3 equals 1 divided by 1 cubed, which again is just 1. So therefore 16 times 1 is still 16. Minus 1. We can add all these terms together. We have 24 minus 2 is 22. Minus 16 is 6. Minus 1 is 5. And then we have a 2e squared next to it as well. That is an exact number. You can throw it into a calculator if you want, but usually any question that's asking you to find something related to this will be absolutely fine for you to leave the e's and the x's, or numbers that don't really agree with each other and can't add and subtract the same ways, they're more than happy for you to leave them separately like that. But anyway, that's differentiation by the power rule. I hope that made sense. If there's any parts that didn't make much sense, indices, square roots, surds, whatever have you, I'll be more than happy to make a video if you just let me know down below. In the meantime, I hope you enjoyed and found that simple, right?